Alright, so first I would like to say a few words about this image here. The reason why we have this image is not random. It is because evolution strategies are based, as I told you, on genetic algorithms, which consist of finding an optimal population of parameters which will lead to the best score that you define through an objective function or a score function. And so, of course, for our case, well, the score is the reward. Our goal is to maximize the reward, which is closely related to the score that you saw when we did this first race at the beginning of this course. And as you probably guessed, well, the population of parameters that we have to optimize is exactly the parameters that we have in this controller matrix, this single layer linear model. And so all the little bears that you see here are exactly these parameters. Some will die, they won't be the optimal parameters, and some will survive to, in the end, give the best parameters. This is, of course, the best parameters. It is the one that will stay the longest in the air. So you see the idea? The goal is to find the optimal parameters in a population of original parameters. Alright, and now, if we start the article, well, you have first an introduction which explains the motivation of using evolution strategies, and it clearly states that it is an alternative to, well, stochastic gradient descent, where we calculate the gradients to, optimize through backpropagation. I think it is explained here somewhere. Here it is, the backpropagation algorithm to, update the weight or, same the parameters to minimize the loss function, the objective function. And so ES is an alternative for RL tasks. And if you scroll down below, you will see that OpenAI published this paper called Evolution Strategies as a scalable alternative to reinforcement learning. Indeed, in reinforcement learning, what we mostly do is that we use the backpropagation algorithm with stochastic gradient descent optimizers like Adam to update the weights in order to reduce that loss error between the predictions and the targets. But here, evolution strategies is a very different technique. It will not use backpropagation at all. It will rather use genetic algorithm-based techniques, which starts with an original population of parameters, will figure out the best ones inside, and then by sampling them, they will get closer and closer to the optimal solution. We will see that right away with actually this first section, what is an evolution strategy. Alright, so our starting point here is to understand what is this? What is this function called the Rastrigian function, and also this one, the Schaefer-2D function. So, as many branches of AI, well, you will have what we call evaluation frameworks. And these functions here are exactly some evaluation frameworks in the sense that they can evaluate different optimizers. Because indeed, what you see here is actually a function that you have to optimize, meaning of which you have to find the maximum. And the very important particularity of this function is that it is, remember this, not convex. Because if it was convex, it would be extremely easy using very simple techniques like just gradient descent to find the maximum or the minimum. But here, as we can clearly see, it is not convex because it has a series of mountain shapes which therefore result in having a lot of local optimum, local minimum and maximum. So a classic technique like gradient descent would not be able to find the global maximum, and that's why the title of this graph is two-dimensional Rastrigian function has many local optima. And so we have to use some other techniques, and these other techniques are of course evolution strategies. So now let's move on to these graphs. What you see on these graphs is a projection of this, so this is the projection of this in a 2D plan. That's why it is called a Rastrigian 2D function. And so what's important to understand now is that the lighter the color is, the closer we are to the maximum. But as you can see, we have here some lighter points which are neighbors to darker points, redder points, and that's how we can clearly see, even in a 2D plan, that indeed we have many local optima. However, as you can see, the closer we get to this area here, well, the lighter it is, and therefore the closer we get to the global maximum, which is the optimal goal. And then make sure to understand that here the axes are x and y, and the color and how light it is represents the z axis here, which is given by f of x and y, and which gives actually the height of that function. And so now, what do we have to optimize? What are the parameters that we have to figure out? Well, these are exactly x and y. Our goal is not to find the maximum f, our goal is to find the parameters x and y that will lead to this maximum f. And so this is a simplification to explain the intuition, but x and y are actually, in the full world model, well, the parameters, or the weights, inside this single layer linear model of the controller. And then this f here is exactly that score function that we have to maximize, or it is that expected cumulative reward of the agent that we have to maximize. All right, so it is very important to understand this. The goal of the evolution strategy techniques will be to find the optimal parameters x and y, which will lead to that maximum. And this is another example. You don't have the 3D shape of the Schaefer function, but we can clearly see that here we alternate between red circles and yellow circles, meaning that we clearly have those mountains here, which however becomes higher and higher mountains until we reach the highest mountain, leading us to the maximum. And for each of the evolution strategies technique, we will see the way it is getting closer and closer to that maximum. All right, then you have the basic process of the evolution strategy. That is the case for each of the ES optimizers. This is coded in pseudocode, and so while true, so this is just a boolean which will allow us to end the loop when needed. The first step is to ask the evolution strategy to give us a set of candidate solutions, meaning a set of candidate couple of parameters x and y. So basically we start with a set of candidate parameters. Then we create an array to hold the fitness results. Then we evaluate the fitness for each given solution, meaning we're going to see which parameter solutions give us high values of the function f, meaning high scores. Then we will give that list of fitness result back to the ES optimizer, from which we will get then the best parameters and fitness scores from that ES optimizer. And depending on the optimizer used, we'll have some threshold so that when we have a best fitness reached over the required fitness, then we will stop the loop. And so all these functions that you see here in pseudocode, well, you have the same ones in the real code in the ES toolkit. For example, this ask function, you'll see it in the ES optimizers. So these are not the ES optimizers here. These are the SGD ones. But for example, let's start with the CMAES optimizer. Well, as you can see, you have this ask method here that exactly asks the CMAES optimizer to give us a set of candidate solutions, meaning a set of parameters x and y in the article, or a set of weights of the controller in our case. So you have the ask method here, but then you also have the other ones like the tell method that gives the list of fitness results back to ES. Here it is, the tell method, before we get the parameters with the best scores. Then same for the genetic algorithm. You have the ask method here, the tell method, and same for OpenES and the PEPG optimizer with the ask and tell. So you can see that this is the common process between the optimizers, and then of course you will see that lots of details change from one to the other. So let's go back to our article and let's start with the first one, the simple evolution strategy. So we'll do that in the next tutorial because we have to take a little break here. Then we'll do one tutorial for each of the optimizers, starting with simple evolution strategy, then simple genetic algorithm, then we'll cover the CMAES optimizer, and finally the last ones, OpenAI ES and PEPG. And of course we'll go back and forth the post and the code to see the parallel with what we're doing. And so now, as soon as you're ready, let's tackle the first one, simple evolution strategy. I recommend to read that first before we see that together. Until then, enjoy AI.